Hello my dear students, I warmly welcome you to Sia's digital classes. In this lecture, we are going to discuss about one of the important theorem on permutation. Let's see what is the statement of the theorem first of all. The name of the theorem is disjoint cycles commute. Okay, in the name only we have disjoint cycles commute. Commute is nothing but commutative property. Okay, to show that any group is going to satisfy the abelian group, we have to show that that group also satisfies the commutative property. Okay, that is with respect to multiplication, a into b is equal to b into a. With respect to addition, a plus b is equal to b plus a. Now the same commutative property we are going to prove in the permutation. See the statement of the theorem. If the pair of cycles alpha is equal to cycle notation a1 a2 up to some a suffix m and beta is equal to b1 b2 up to some beta suffix n have no entries in common. Have no entries in common means that there is no common element in between these two permutations, or else are any two disjoint permutations. Okay, in the examination question will ask in this format also, have no entries in common or any two disjoint permutation, then we have to show that alpha into beta is equal to beta into alpha. This is the commutative property with respect to multiplication. Okay, so now see the proof of this theorem. First of all, given First of all, given alpha is equal to a1 a2 up to son a suffix m and beta is equal to b1 b2 up to son beta suffix n are the two disjoint cycles, two disjoint permutations, okay, of the one finite set capital S. Capital S is equal to, we can write here a1 a2 up to son a suffix m, b1 b2 up to son b suffix n and c1 c2 up to son c suffix s. Okay, so it is a finite set. Here the set S contains finite number of elements. Okay, so and also the elements c suffix i's are fixed. Okay, and also the elements which are represented by the c suffix i's, that is c1 c2 up to c suffix 6, are fixed. Okay, so which are left untouched by the both permutations alpha and beta. Okay, here the sum of the elements in capital S c suffix i's are fixed. Okay, fixed means those are the constants. Okay, fixed elements, those are untouched by the given two permutations alpha and beta. Now to prove this theorem, to prove alpha into beta is equal to beta into alpha, it is enough to show that alpha into beta of x is equal to beta into alpha of x for all small x belongs to capital S. Okay, so we have to prove this equation, alpha into beta into x is equal to beta into alpha into x for all x belongs to S. So that is only our claim. So now I am taking case 1. Okay, in case 1, here small x belongs to S. Okay, that means, so in case 1 we can take x belongs to a suffix i's. Okay, so same x in case 2 we can take x belongs to b suffix i's, and the next case 3 same x belongs to c suffix i's. So by taking these three cases, okay, with respect to x belongs to S, so we have to prove this equation star. Okay, then we can clearly say that the disjoint cycles will satisfy the commutative property alpha into beta is equal to beta into alpha. Let's see the first case. Let x belongs to a suffix i's. That means x is equal to a1, a2 up to so on a suffix m. Okay, then okay, from equation star, then from equation star we can write LHS alpha into beta of x is equal to alpha into beta of a suffix I. So therefore alpha into beta, beta into a suffix I, alpha into beta, beta into a suffix I. Here beta is the one disjoint cycle. In that beta we have b1, b2, b3 up to some b suffix n. Only b elements are there in beta. Okay, there is no other a elements, there is no c elements. So therefore if you write only b elements only, then beta will count them. Otherwise the rest of the elements considered as a constants. So therefore now here beta into ai you can write as it is alpha into ai. Why? Because since beta fixes a suffix i's. So therefore next in the next step you can write alpha into beta into x is equal to, we have alpha into ai. So from the one of the noun theorem, that is every permutation can be represented as a disjoint cycles. From that theorem you can write the direct formula alpha of a suffix I is equal to a suffix I plus 1, a suffix I plus 1. That is the LHS value. Next RHS. So RHS is nothing but beta into alpha into x. So therefore beta into alpha, what is the x? A suffix I. So therefore the next page, so that implies beta into alpha into a suffix I. So according to the noun theorem you can write this value as beta into a suffix I plus 1. Why? Because alpha is a permutation, okay, having the same elements a suffix 1, a suffix 2 up to a suffix m. Then that value gives that a suffix I plus 1. So therefore again we got beta into a suffix I plus 1. So therefore then you can write a suffix I plus 1 only. Why? Because beta does not count the a suffix I values. Beta counts only b1, b2s only. Okay, beta does not count a1, a2s. Beta does not count c1, c2s. Beta will count only b1, b2 up to some b suffix n only. Okay, since you can also clearly mention that beta fixes a suffix i's. Okay, that is the condition. In both LHS and RHS we got the same value. So therefore LHS is equal to RHS in this case. So therefore alpha into beta into x is equal to beta into alpha into x. That is taken as equation number 1. Now you can go to the case 2. Okay. So in case 2, let I am taking small x belongs to b suffix i's. Okay, I am taking small x belongs to b suffix i's. b1, b2 up to some b suffix n. Now LHS. From equation star you can write the LHS alpha into beta of b suffix I. Okay, is equal to alpha into beta of b suffix I. Beta of b suffix I. So therefore alpha into, here you have beta and b1, b2. Okay, the same set only. So then you can write the formula according to that. So b suffix I plus 1. Okay, since we wrote here a suffix I plus 1. See, here we are writing b suffix I plus 1. And again we got alpha into beta I plus 1. So therefore here alpha fixes beta values. Why? Because in alpha only a1, a2, a3 up to some a suffix m only will be there. There is no b terms. So therefore alpha fixes b terms. So therefore you can write that b term as it is. Okay, b suffix I plus 1. So that is the LHS value. Next you can take RHS in this set. Beta into alpha of b suffix I is equal to beta into alpha of b suffix I. Alpha of b suffix I. So that implies beta into, here you have reverse elements alpha and beta. So therefore alpha and bi. So therefore you can write b suffix I as it is, and again we have beta into b suffix I. You can write b suffix I plus 1. Here also we got the LHS is equal to RHS. So therefore LHS is equal to RHS. You can say that alpha into beta x is equal to beta into alpha into x for all x belongs to beta i's. Okay, so this is taken as equation number 2. So now in case 3, let now I am taking x belongs to c suffix i's. X belongs to c suffix i's. Whenever you take x belongs to c suffix i's, then alpha and beta fixes c suffix i's. That means, okay, so you can take that LHS. So therefore alpha into beta of c suffix I. I am taking directly in place of x c suffix I. So therefore alpha into beta into c suffix I. So therefore alpha into, here beta contains b1 b2's only. There is no relation with c1. So therefore you can write c suffix I as it is. Okay, and again we have alpha into c suffix I. There is no relation with c i's with alpha. So therefore again you can write that value c suffix I only. That is the LHS value. Next to RHS you can write beta into alpha into c suffix I. So therefore you can write beta into alpha of c suffix I. So that implies beta into again c suffix I you can write. So therefore again c suffix I. Why? Because from this condition alpha and beta fixes c suffix i's. So therefore in both cases, okay, in case 3, in LHS RHS we got the same result. So therefore you can write that LHS is equal to RHS in this case also. So therefore alpha into beta into x is equal to beta into alpha into x for all small x belongs to c suffix i's. This is taken as equation number 3. So therefore from equation number 1 and 2 and 3, we can clearly say that alpha into beta into x is equal to beta into alpha into x. Okay, for all x belongs to capital S. So therefore finally you can say that alpha into beta is equal to beta into alpha by taking the right cancellation law. Okay, I clearly told you in the previous lectures regarding the elementary properties of the group. Whenever we are discussing about the elementary properties of the group, one of the condition is cancellation laws. Okay, while solving the theorems and problems upcoming units, so therefore we can use the left cancellation law and right cancellation law. Here by using the right cancellation law, you can cancel small x on both sides. Then you can say that alpha into beta is equal to beta into alpha. You can write, since you have to mention that one, since by right cancellation law, you have to mention this word. Why? Because we are using that algebra conditions only to solve the algebra theorem. So therefore since by right cancellation law we are getting alpha into beta is equal to beta into alpha. So this gives the, so therefore disjoint cycles commute. Disjoint, where alpha and beta disjoint cycles, now therefore disjoint cycles commute, satisfies the commutative property. So this is the proof of the theorem. In the previous lecture only we discussed that the symmetric group S suffix n, okay, the symmetric group S suffix n does not satisfy the abelian group property. Okay, yeah, symmetric group S suffix n for n greater than or is equal to 3. Okay, from starting S3, S4 up to so on S suffix n. In the previous lecture we proved that there is no condition alpha into beta not is equal to beta into alpha. But in this lecture we proved that alpha into beta is equal to beta into alpha. You have to realize, you have to recognize the difference between these two theorems. Okay, symmetric group does not satisfy the commutative property, but disjoint cycles satisfies the same commutative property with respect to multiplication. That is the difference between these two theorems. Okay, so I hope you understood this theorem very well. Okay, so make a perfect practice. In the next lecture we are coming with another topic. So until bye, thank you.